Okay, so I want to discuss sums of the form, the sum of n to the r from n equals 1 to big N, where r is some positive integer. So for example, for r equals 1, we have that the sum of n from n equals 1 to big N is famously n times n plus 1 over 2. For r equals 2, maybe a little bit less known, but still fairly common, is that the sum of n squared is n times n plus 1 times 2n plus 1 over 6. For r equals 3, we have the sum of n cubed from n equals 1 to n. This is maybe even less known, but it's actually easier than the 2 case. Turns out to be the 1 case squared. And I think, I used to think, and I still think that this is sort of a special case, but there's some sort of way that you can generalize this to other cases where powers of this are some other combinations of such sums. You can see that on Wikipedia. Maybe we can look at a degenerate case where r equals 0. And if we take the sum of n to the 0, then this is just taking the sum of a bunch of 1s. And so here, what we get is simply n. Now here, these formulas I sort of memorized back in high school for math competitions, but how do you even figure out like a general formula for this? So if you want to figure out what is the sum of n to the r, how do you figure that out? In particular, for example, how can we figure out r equals 4 or r equals 5? There's no clear pattern of what's going on here. Maybe you can work hard and figure out a clear pattern, but it's not so clear on the onset how to do that. So I'm going to show in this video that there is a general formula that involves these numbers called the Bernoulli numbers, and sort of a not really good mathematical way of getting it, but it is a nice sort of derivation using infinite sums and divergent series, sort of Euler style. Now, I was led to that from my last video on deriving the zeta function and relating that to, or relating values of the zeta function to Bernoulli numbers using some sort of underhanded tricks. And I'm going to do some similar things here, but before I get to that, let me show you maybe how you could have worked at least these cases out on your own and how you can do a general case, even if it's a bit tedious. So one thing to note is that you can figure out the leading coefficient by saying that the sum of n to the r from n equals 1 to n is approximately the integral of x to the r dx. And the reason for this is just that if you were to graph this out, x to the r sort of looks like this polynomial graph, and then the sum that you're taking is just like the sum of these blocks. And then as you take n to be a very large number, these sort of error things in between become very small in comparison to what the total sum is. So you should get that the leading term is 1 over r plus 1 n to the r plus 1. So what you should have, and we can actually see that from our examples here, where for n equals 1, we have the leading term is n squared over 2. For n equals 2, we expect 1/3 n cubed. What we end up with on top is 2n cubed, but we're dividing by 6, so that's n cubed over 3 as we expect. Over here, the leading term is n squared squared, so that's n to the 4th divided by 2 squared, which is 4. And over here, even for 0, we have n to the 1st over 1. So that all agrees. The question is, how do we get these smaller ordered terms? So what we can say, for example, is that we expect that this is some polynomial. So we just make a guess that this is equal to 1 over r plus 1 n to the r plus 1 plus some coefficient times n to the r, say, plus some other coefficient n to the r minus 1, and other lower order terms. You want to compute what these coefficients are. So before I show you the general trick to figuring out what these coefficients are, let me first show you how you might proceed with this by hand. So what you can say is, well, what if I take the difference of two of these? So I say I'm going to go up to big N. I'm going to say I'm going to go up to n minus 1. And here, because you're just adding on one new term, you already know what this difference is going to be equal to. It's going to be equal to big N to the r. On the other hand, you can take the difference of this sum and substituting in n minus 1 for this sum, you get something like 1 over r plus 1 n to the r plus 1 minus n minus 1 to the r plus 1 plus a n to the r minus n minus 1 to the r plus b times something, and so on and so forth. And you can inductively then figure out what these coefficients are as follows. So what you can do is you can binomial expand this n minus 1, and you can say that this one is n to the r minus r plus 1, sorry, n to the r plus 1, but minus r plus 1 n to the r plus r plus 1 choose 2 n to the r minus 1, and so on and so forth. So it's just binomial expansion. And then what happens is this n to the r plus 1 cancels with this guy. And what you're left with is these minus signs cancel, and you have an r plus 1 here, which cancels with this r plus 1. What you're left with is n to the r, which is what we expect to get on the left. So this sort of shows you why this coefficient of r plus 1 has to be there from another viewpoint. That is just to cancel out this r plus 1, which comes from binomial expansion. And in fact, you can figure out the higher order terms as well, or sorry, the higher coefficients from this as well. And the way to do that is to say that here we get an extra term, which is n to the r minus 1. But we shouldn't have such a term because no such term appears on the left. So instead what we can do is we can expand this side. And we get here is a times n to the r minus, and only expanding this, we get n to the r minus r n to the r minus 1 plus other stuff. And so this n to the r and n to the r cancels, and this minus sign becomes a plus. And we get left with is these two terms, r plus 1 choose 2, 1 over r plus 1 with the negative sign, which comes from there, times n to the r minus 1 plus a times r, minus signs cancel, n to the r minus 1 is equal to 0. Why is equal to 0? Because there's no n to the r minus 1 term on the left, and you can convince yourself that there's no other possible contribution of n to the r minus 1 from the other terms. And so this gives you, well, this is r plus 1 times r over 2. R plus 1 cancels. You can divide by the r, and so you get that a is equal to 1/2. Right? And that agrees with these terms, where here you have, for example, n squared plus n over 2. Here you can also show that the subleading term, so the coefficient of n squared here, would be 1/2, and so on and so forth. But now as you go to the next term, then you have to say, okay, well, you're going to get an n to the r minus 2 term here. You're going to get an n to the r minus 2 term over here, and these coefficients are fixed. Now you have to introduce this b variable for the n to the r minus 1. And over here, you're going to get some contribution of n to the r minus 2 with the highest order term canceling just like we had here. And then you solve for b, and then you solve for the next one, c, and so on and so forth. And so you can see that kind of becomes a little bit of a tedious process that you have to do every time. And this fact that a equals 1/2 is sort of convenient, but turns out it's not always the same number for all of these, like for all values of r, and so you have to like solve a different problem each time. So now, with that sort of standard way of doing it out of the way, let me show you what I'm going to do in this video, which is sort of extend the sum out to infinity and then contract off the rest, and somehow that'll actually make things easier. So this was inspired by the last video where I showed that zeta of 1 minus n is equal to minus bn over n, where bn are these numbers defined as follows. If you take the series t over e to the t minus 1, then this is equal to the sum of bk over k factorial t to the k, from k equals 0 to infinity. So you just binomial expand this function, and then you take these coefficients. So this k factorial is just like sort of a normalizing factor, which makes things convenient. If you saw the other video, then you would know why. If you don't remember the tricks that I used for that video, you should watch that video because I'm going to use a lot of the same tricks here. But anyways, the main point that I used in that video was this fact that s times zeta of 1 minus s, which is quote unquote equal to s times the sum from n equals 0 to infinity of n to the s minus 1, this is equal to d over 1 minus e to the d times x to the s evaluated at x equals 0. And so remember, the idea was that this 1 minus e to the d, you can literally expand that into 1 plus e to the d plus e to the 2d and so on and so forth. And we're using this key fact that if you multiply f of x by e to the d, then this is equal to f of x plus 1. Or if you repeat this process, then e to the n df of x is equal to f of x plus n. And this is sort of reincarnations of Taylor's formula. And then if you differentiate this with a d, then you pull out an s, and then you get sum of n to the s minus 1. And this d, you can do without it. It's just so that you get this definition of the Bernoulli numbers. At the end of the day, the numerical factors would be the same. It's just that you'd get sort of different algebraic expressions if you didn't include the d there in the derivation. But sort of here, what we have is kind of nice. Maybe I'll say that in a moment. What I'm going to do now is say that I was making that video. I thought afterwards, the sum is a lot like this sum, except this goes off to infinity and this one doesn't. So what if we just take the difference of these two things? So what I'm going to evaluate here is s times the sum from n equals 0 to infinity of n to the s minus 1 minus the sum from n equals n plus 1 to infinity of n to the s minus 1. And so here what happens is, because we're taking the sum from 0 to infinity minus the sum from n plus 1 to infinity, all we're left with is the sum from n equals 0 to n. So putting parentheses around that, this is equal to s times the sum from n equals 0 to n of n to the s minus 1. And sort of this is like this is sort of nice, because here the s times zeta of 1 minus s, we saw that we started sort of with zeta of negative s, but then we modified to this so we can get to the Bernoulli numbers. But this is also sort of the right normalization here, because this will look like s times n to the s over s, which is n to the s. So the leading order term here will actually be like 1 plus the exponent divided by s. So it's sort of a nice leading order term. I'm not sure of the history of the thing. I'm pretty sure these Bernoulli numbers actually came out of applying this first, and then it was realized later that it also relate to the zeta function. But it's kind of nice that these two things work out in the same way. So what I'm going to do here now is just manipulate this similar to what I did in the other video, and get something similar to something to do with the Bernoulli numbers, and then show how you can find explicit formula for this expression. Okay, so what I'm going to do with this is to say the same thing in the last video, is that this is the sum from n equals 0 to infinity of x plus n. So I'm going to raise this to the power of s. I'm going to take a derivative. And this derivative is derived with respect to x. What that does is it pulls down the s here, and then changes the exponent to s minus 1. And at the end, I'm going to set x equal to 0. So then this is just the sum of n to the s minus 1 times s. Okay. And I'm going to do the same thing over here. Take the sum from n equals n plus 1 to infinity of d x plus n to the power of s. Then evaluate all of this at x equals 0. So now I'm going to modify this a little bit. And I'm going to say, instead of having the lower limit as n plus 1, that sort of becomes annoying when you're trying to deal with a geometric series. It's always convenient when you have a geometric series starting at n equals 0, because then the first term is just 1, and you end up with like 1 over 1 minus x, or something like that, right? So what I'm going to do is I'm going to rewrite this as a sum from n equals 0 to infinity of d x plus n to the s minus the sum from n equals 0 to infinity of d x plus n plus 1 to the s. All of that value at x equals 0, taken at the end of the day. Okay. Now I'm going to apply the same trick from the last video, where I'm going to say this is the sum from n equals 0 to infinity. Using this formula, we can rewrite this as d e to the nd x to the s. So this is just going to change this x to the s to x plus n to the s. So this is the same thing. And then minus sum from n equals 0 to infinity of d. So here what I'm going to do is I'm going to write this as follows. E to the d, e to the nd, x plus n to the s, evaluated at x equals 0. So why did I choose to write it like that? So this e to the nd is going to bring out this little n, and this e to the d is going to add this plus 1. So again, these two things are just the same thing. But the first time I was doing this, I just sort of kept it in terms of n plus 1, but you get some n plus 1 terms versus capital N, and it's just nicer to have capital N. I could recommend that you try this calculation out, calculation if you can call it that, and instead don't have this e to the d there and see what you get. But anyways, what we can do now is we can sort of see that we have these Taylor series or these geometric series of e to the n d here. And so we can rewrite this as d over 1 minus e to the d x to the s minus, here we have a d e to the d, so we have that extra guy. So we have a d e to the d over 1 minus e to the d times x plus n to the s by x equals 0. Now you may say that, okay, over here we have like negative, the generating series for the Bernoulli numbers, but over here we have something a little bit different. It's not so clear how multiplying by this e to the d changes things. It might change up the coefficients a lot. So you might worry that we've strayed quite far from the Bernoulli numbers. But in fact, this function has a remarkable property that if you take t over e to the t minus 1, you just add t, it's going to be equal to t e to the t over e to the t minus 1. So the reason for that is that you add a t, if you just divide and multiply by e to the t minus 1, you get a t e to the t minus t. The minus t cancels with the t over here, and you get this guy. So there's sort of two conventions for the Bernoulli numbers. This is the sort of original one, and this is a different one. And on the Wikipedia page, the only thing that's different between these two is the coefficient of t, which we'll see later that this one has a coefficient of negative 1/2, this one has a coefficient of positive 1/2. So I think in the other video for the zeta function, I accidentally said it's saying that b1 is equal to 1/2, which just comes from this one. But I should have said it's negative 1/2, which comes from this series. But I'll do some computations later, and we'll see how to get the Bernoulli numbers sort of computationally, at least the small ones, and see what the discrepancies are here. But the only difference of these from the Bernoulli numbers is in b1. All the other Bernoulli numbers are the same. So I'll call this series expansion bk plus over k factorial because we're adding a t there. Same convention that's used on Wikipedia. Call this bk minus. Okay, so if we do that, then I'm going to rewrite this over here. This is equal to, well, we can Taylor expand this, and this is the sum from k equals 0 to infinity of bk minus over k factorial, because this is the t over 1 minus e to the t with a negative sign, because here it should be e to the t minus 1, here it's 1 minus e to the t, x to the s, and then minus, let's see here, Taylor expanding this now. This is the sum of bk plus over k factorial. I forgot the d to the k. D to the k, x to the s. Sorry, x plus n to the s. Evaluated at x equals 0. So hopefully that's right. Taylor expand this, multiply by x to the s. Taylor expand this, multiply by x plus n to the s. Yep, that seems about right. And over here, again, because it's 1 minus e to the d instead of e to the t minus 1, the minus minus cancels out, and we get a plus sign over here. Okay, so we saw in the other video on the zeta function that if we take dk x to the, let's say now that s equals r, which is an integer. So if we take dk of x to the r and evaluate at x equals 0, then this is equal to, well, for k greater than r, it's 0 trivially because we're taking more than r main derivatives. But we also saw for k less than r, this is also equal to 0 because we're evaluating at x equals 0. So this is non-zero only for k equals r. And in that case, what it is equal to is we're taking k derivative, or we're taking r derivatives of x to the r. And so we end up with is r factorial. And when we evaluate x equals 0, that doesn't do anything, it's just a constant. So what we end up with is minus br minus for this first term over here. The second term, however, what we have is dk x plus n to the r by x equals 0. Now the thing is, this is still equal to 0 for k greater than r, because that's a bit confusing to read. This is equal to 0 for k greater than r because we're still taking more derivatives than we have exponents, right? And this is just an integer. But for k less than or equal to r, this is not necessarily 0. So what is it equal to? Well, we can write it out. This is the sum of bk plus over k factorial from k equals 0 to infinity of, well, if you take one derivative, you're going to pull out an r. So here I'm saying s equals r, which is some integer. So if you take one derivative, it's going to be r times x plus n to the r minus 1. If you take two derivatives, it'll be r minus 1. And then you keep on taking derivatives until you get r minus k plus 1 times x to the x plus n to the r minus k, evaluated at x equals 0. So let me see if I did this correctly. If I take one more derivative, then it would be r minus k over here. And yeah, okay, so I think that's right. Okay, so now we can conveniently write this as minus br minus plus sum from k equals 0. So actually here, this upper limit shouldn't be infinity. This upper limit is infinity. But this upper limit we can just take to be r. Why? Because as I said, if k is more than r, then this is 0. So now here, this is where we get a finite sum. So we've gone from divergent series to something which is actually finite and controlled. And what we have here is k equals 0 to r. What is this expression? Well, notice that here we can take this factorial all the way down to 1 if we divide by an r minus k factorial. And so then what happens is that this is just r choose k. Okay? Now we have this bk plus. And now, here's the interesting part. If we plug in x equals 0, we don't get 0 anymore. What we get is some residual term, which is n to the power of r minus k. Right? And the last thing to notice is that I'm going to say ignore r equals 1, which is the only discrepancy between br minus and br plus. We'll discuss that later on. But notice that that corresponds to the sum of n to the power of 1 minus 1, which is 0. So that'll be this term. And so it's not really too important. We know how that one works. But for all other terms, this is the same thing as br plus. So I'll just ignore the superscript now. And notice that when we plug in k equals r here, we have r choose r, which is 1. We have n to the power of r minus r, which is also 1. So that term just sort of drops out. So we get is the sum from k equals 0 to r minus 1 of r choose k, bk plus n to the r minus k. And so finally, what we get is that s times the sum from n equals 0 to n of n to the s minus 1, which we've gone lost a little bit, comes from over here, which is the same thing as everything that's been written down, is equal to the sum from k equals 0 to, I should write this as r because we're using r for the integer, k equals 0 to r minus 1 of r choose k, bk plus n to the r minus k. Right? Or alternatively, if you wanted the original thing, then we have that the sum of n to the r from n equals 1 to n, or 0 to n, whatever you want. This is equal to the sum from k equals 0 to r. Here I'm just adding 1 to everything, of 1 over r plus 1, r choose k, bk plus n to the r plus 1 minus k. And that is our final formula. So I'll end this off with doing some sample computations involving this. So we'll see that we recover all of the formulas that we've seen already, and also get some new formulas for r equals 4 and 5. So let me rewrite this out. So at this point, I think you should be feeling a little bit at least suspicious or uneasy because, for one thing, this is mathematically illogical because we're just taking the difference of two infinite things and sort of gone this finite thing. But mathematics is sort of forgiving in a sense that if you didn't do anything too outrageous, then magically you'll get the right answer at the end. But this is still sort of a funky thing, right? How do we actually compute with this? But I'll do some computations and hopefully it should start to convince you that this is actually a true statement. So remember that these coefficients are defined by taking the power series t e to the t over e to the t minus 1 is the sum of bk plus over k factorial t to the k. And actually, this is also equal to, as I said, t plus t over e to the t minus 1. So what I'll actually do is I'll compute these coefficients over here. Okay, so how can we do that? Well, Maybe this will be a little bit intimidating to you, but I'll show you that's not that bad. At least, well, there are much more efficient ways to do it, but like there is a way that you can at least compute these. So we know what the Taylor series approximation of e to the t minus 1 is, and that'll be like 1 plus t squared over 2 plus t cubed over 6 and so on. So this is just equal to t over, if you subtract 1 from that, then that'll just be t plus t squared over 2 plus t cubed over 6 and so on. What we can do is we can divide the numerator and denominator by t, and we get 1 over 1 plus t over 2 plus t squared over 6 and so on. So this is like t to the n over n plus 1 factorial. And if we sort of consider all of these guys as a unit, then we can do the sort of one power series that everyone should know, which is the geometric series. And we get that this is 1 minus t over 2 plus t squared over 6 plus so on and so forth, plus t over 2 plus t squared over 6 plus t cubed over 24 and so on squared minus the same thing cubed plus the same thing to the 4th power and keep on going, right? Okay, so how can we actually explicitly compute these? So for example, if we look at b0, then this is just the constant term, which is just 1, okay, cool. If we look at b1, here's where we have to be a little bit careful. Remember, this is b1 minus, and it's b1 minus over 1 factorial. That's not too important because 1 factorial is just 1 here. But how do we compute this? We just look at the coefficient of t. So here, everything will have an exponent at least 2, here exponent at least 3, here exponent at least 4. So the only coefficient of t comes from this first term, which is negative 1/2, right? Because this is minus t over 2. Now, b1 plus is then equal to b1 minus plus 1 because we've added a t over here, which is equal to positive 1/2. Okay. Great. So now, what is b2 over 2? Well, we look at all terms which have a 2 going on in them. So this is t squared over 6 with a negative sign. And then over here, we get a t over 2 squared with a positive sign. So what we get is that this is 1/4 minus 1/6, which should be equal to 1/12, I think. Yep. And so then what we end up with is that b2 is equal to 1/6. Okay. And I won't compute b3 because b3, b5, b7, and so on, they're all equal to 0, it turns out. And one way to see that, I'll leave it as you to see that, but if you take this term, and you add them together, then, or subtract them, that sort of looks like the denominator. So you can check that if you add 1/2 t, which is the coefficient of b1 minus, to t over e to the t minus 1, then you end up with an odd function. So this is a function which is not at all obvious that it's close to being odd, but it's very close to being odd. And so I'll leave that to you to check that all the odd Bernoulli numbers are 0. Yeah. So in that case, let's see what b4 is equal to. So what sort of terms are we going to get? Well, over here, we're going to get one term, which comes from t over 2 to the power of 4. Over here, it turns out the only way that you can get exponent of 4 is by taking t over 2 squared times t squared over 6. So you get a t over 2 squared times t squared over 6. And this is a term in a trinomial expansion, which is of the form a squared b. This comes with a coefficient of 3 and a negative sign. Right? Over here, we can get 2 possible ways of getting exponent of 4. And so that is, we can do t over 2 times t cubed over 24. Or we can do t squared over 6 squared. So again, all I'm doing here is, for each of these terms, since this is something squared, I'm picking 2 of these monomials and seeing when can I get the exponent to be 4, for example. Here I'm taking 3 of the monomials, seeing when can I get the exponent to be 4, or whatever exponent you're looking for. And over here, since we have a term of the form ab from a binomial squared, this will come with a coefficient of 2 and an overall positive sign, so that's fine. And then over here, we get a term which looks like t to the fourth over, well, it will be 5 factorial, which should be 120 with the negative sign. So what we end up with is b4 over 4 factorial, because that is what the coefficient is going to be equal to negative 1 over 120 plus 2 over 48 plus 1 over 36 minus, this would be 1/4, 24 minus 3 over 24 plus 1 over 16. And if I did the calculations correctly, check on a calculator, maybe I did it wrong, but hopefully I did right. It should come out to 1 over 720. And so 4 factorial is 1 over 24. So 4 factorial is 24, and so this implies that b4 is equal to negative 1 over 30. Okay, so here's how you can compute Bernoulli numbers in case you were ever scared about computing them. Now we can plug this into our formula and finally get out nice answers. So let's say, again, r equals 1. We should test out cases that we know to make sure that it works. So the claim is that the sum from n equals 1 to big N of n is equal to, well, okay, so 1 over r plus 1 is 1/2. And now our k equals 0 term is just 1 choose 0, which is 1, times b0 times, I'm going to drop the exponent now. It's always these bk plus exponents, these bk plus terms, times n to the power of 2 minus 0, which is just n squared. And then you are adding on 2 choose 1, which is, sorry, this should be r plus 1, I believe. Yeah, messed up a little bit there. Over here we have an r choose k, so over here we should have an r plus 1 choose k. 2 choose 1 times b1 times n to the power of 2 minus 1. So that's n to the first. And so what we end up with is 1/2 times n squared plus 2 times b1 plus is also 1/2. So that's 1/2 times n squared plus n. It's n times n plus 1 over 2. Okay. Now r equals 2. You have the sum from n equals 1 to n squared is, it should be 1/3 times 3 choose 0 b0 n cubed. And then now, once you get into rhythm of things, it's not too bad. What you do is you write out the binomial coefficients, and then you keep increasing the subscripts and decreasing the exponents. And you stop right before the last term. So one thing to know is that there's no constant term that comes from the final Bernoulli number cancellation that we did at the end. And that makes sense because if you take the sum of nothing, then you should get 0. So what we end up with here is 1/3 times 3 choose 0 is 1, b0 is 1, so this is n cubed plus 3 over 2. 3 is from this, times 1/2, n squared, and then b2 is 1/6. This is also 3, so this is plus 3 over 6 n. And we can sort of factor things out, and what we should end up with is, well, we can pull out an n, do n over, so you write this as 1/2, so n over 6 times n squared 2, wait, sorry, n over 6 times 2n squared plus 3n plus 1. All I did is I divided this by 2 and multiplied by 2, and then factor out the n over 2. And then this is n times n plus 1 times 2n plus 1 over 6. Hopefully you can see that this factors as 2n plus 1 times n plus 1. Okay, r equals 3. Doing the same thing, we get the sum from n equals 1 to n cubed equal to 1/4 times b0 n to the 4th plus 4 b1 n cubed plus 6 b2 n squared plus 4 b3 n, right? And now we can plug in values. So this is 1/4 times n to the 4th plus 4 times 1/2 is 2n cubed. 6 times 1/6 is just 1 plus n squared. And then you can sort of see that b3 is equal to 0, as I claimed earlier, so this is just nothing. And what we end up with is 1/4 n squared times n squared plus 2n plus 1, which is indeed n times n plus 1 over 2 squared. So that's satisfying. Before doing r equals 4 and 5, let's discuss the degenerate case, r equals 0. So here is where the little discrepancy between this br minus and br plus would come in. And so the only thing that I want to point out here is that you have the sum, and it should be n. But if you sort of actually do take the difference of negative 1/2 plus 1/2, which is negative b1 minus plus b1 plus, then this will be n plus 1, right? So maybe this one you can put a question mark. And this sort of comes from is 0 to the power of 0 equal to 1 or 0? And or alternatively, are you starting the sum from n equals 0, or are you starting the sum from n equals 1? So it's sort of this ambiguity that leads to this sort of ambiguity in the formula. Anyways, r equals 4, you can sort of see where the pattern is going. N equals 4, n equals 1 to n. Go to 1/5 b naught n to the 5th plus 5 b1 n to the 4th plus 10 b2 n cubed plus 10 b3 n squared plus 5 b4 n, right? And this is 1/5 times n to the 5th plus 5 over 2 n to the 4th plus, this will be 10 over 6, which will be 5 over 3 n cubed. b3 is 0, and b4 is negative 1 over 30, so that'll be negative n over 6. So you can write this as 1 over 30 times 6n cubed plus 15, sorry, this should be to the power of 5, not cubed. 6n to the 5th plus 15 n to the 4th plus 10n cubed minus n. Hopefully that is correct. And so here, you can sort of factor things out a little bit. So what you get is you get an n. And then you'll notice that if you plug a negative 1 into this, you get negative 6 plus 15 minus 10 plus 1. So these two add up to negative 16. These two add up to positive 16. So negative 1 is a factor. You get n plus 1. I searched up on Google. It turns out 2n plus 1 is also a factor. And then you get something like 3n something, 3n squared, something, divided by 30. And finally, r equals 5. We can do the same thing. Perhaps you're tired of it by now, but it is satisfying because we don't actually have to do any extra work. Because what we end up with is b0 n to the 6th plus 6 b1 n to the 5th plus 15 2 n to the 4 plus 20 b3 n cubed plus 15 4 n squared plus 6 b5 n. And so the reason we don't have to do any work is, again, I claimed that all the odd Bernoulli numbers are 0. So this is just 0. So we get is 1/6 n to the 6th plus 3 n to the 5th plus 15 over 6. So that'll be like 5 halves n to the 4th. Again, this is equal to 0. And this is negative 1 over 30. So that's minus 1/2 n squared. And so you can notice, like, if you try the earlier method of just like brute force trying to take differences of things, it's not so obvious how you can get these coefficients out of it or get a general formula. But over here, somehow, by taking the sum, extending it to infinity, and then subtracting off the tail of an infinite sum, we are able to more easily manipulate this thing and actually get an answer that works at the end, even though it doesn't seem like it should.